Hi, welcome back to my control system lecture. So in this lecture, I'm going to revisit the same example as my previous video to design a controller to achieve a certain specification using root locus method. Now we check here, okay, in the last example, we have designed a lead controller that actually achieves the setting time and maximum overshoot requirement. In this example, I'm going to add with one additional requirement, which is I will need my steady state error to be equals to 0.01 for unit step response. And as you can see here, the steady state error a requirement introduced in this example will require us to change the lead controller to either the lag compensator, or the easier way is to introduce a lead lag compensator, because by using a lag compensator to achieve the time transient requirement as well as the steady state requirement here will be quite challenging. And in this example also, I will also explain that if you use the lead lag compensator approach that we normally see in the online resources or from the books, so there is actually a blind spot. That makes that we may not be able to entirely trust the methods to actually achieve the lead lag compensator. So let's begin on this, okay? First of all, to design a lead lag compensator, as what we have advised earlier, we will have to design the lead compensator first. And the lead compensator we have already explained in the previous example, so you can actually check my previous video on that. So the lead compensator has been achieved. Let's say I denote it as a C1, as that we actually designed in the previous example is 6.36387 S plus 1 over S plus 12. And then now we are going to cascade with an lag compensator, which I'm going to denote as a C2S, and I'm going to give it as a K2 S plus alpha over S plus beta, where alpha and beta will be the zeros and the poles respectively for the lag compensator, and the ratio of the alpha and beta here will be always greater than 1, since for the lag compensator the magnitude of the alpha must be always greater than the magnitude of the beta, so that it can give us a larger ratio than 1 when we actually calculate the Kp or Kv. Let's check out this, okay, the solution on the lag compensator. When we actually designing the lead lag compensator, basically we actually cascade the lag on top of the lead. That means our system will be looking something like this, okay? So we have our C2, which is our lag, followed by C1, which is the lead compensator, connected in series with the G, and then will be the output, minus and plus. And if you want to actually achieve all requirements at one go, we have to ensure now the root locus magnitude and angle criterion that I explained earlier in the lead compensator will remain unchanged even after you add in the lag compensator. That means if I am looking at the angle requirement, the angle of C2, C1, G at the desired root earlier must be always maintained as negative 180, and then the magnitude of C2, C1, GSD must be equals to 1. Okay, in the previous example, we have already ensured that the angle and the magnitude here in the lead compensator design already achieved negative 180 degree and already achieved 1. So how do we actually add something like example C2 in the angle criterion that still make original lead compensator unchanged? In this case, okay, we can conclude that if I want to realize this, the angle contribution by C2 at the SD must be very close to 0 degree. Similarly, for the magnitude of C2 at SD must be approximately equals to 1, so that the root locus, or the more precisely the shape of the root locus of the lag compensator system on top of the lead compensator system remain unchanged. So that means, in short, we just do not wish to change the shape or the dominance of the root locus after we add the lag compensator. And hence, if you are imagining how do we actually be able to achieve this, the solution is very simple. We just need to make sure that the location of the zeros and the poles of the lag compensator must be very far from SD. That means, as long as we choose our zero, okay, we choose the zero of our lag compensator, which means in this case here our alpha, to be very small compared to the real part of SD. So in our previous example, our SD here is equals to -8 plus minus j 8 point something, which is not relevant. So in this case here, as long as I choose my alpha value here to be something less than -8, then my solution here can approximate to a condition that the angle contribution will be close to 0 degree and the magnitude contribution to be approximately equals to 1. Let's begin on the solution here. So we need to make sure that we actually hit the steady state error of 0.01. So this steady state error 0.01 will be equals to 1 over 1 plus Kp. So our Kp, the static positional error constant, will become 99. And this Kp is actually calculated based on this equation s goes to 0, C2, okay, which is our lead, multiply C1 and multiply G S. Okay, so we have here our C2 and then this part will be our C1 and then G. After substitution of all the values here, the Kp must be remain as 99, and then of course K, because of the condition earlier, it is automatic that the K I must set it to 1. So that to realize that the magnitude contribution here must be equals to or approximately equals to 1. So we are now left with the ratio of alpha divided by beta and then multiply 1.7997. So which makes our alpha divided by beta value will be approximately equals to 55. From what we have discussed earlier, we will set the alpha to be at least 10 times smaller than the location of the real part of our SD. That means I will set my alpha to be equals to 0.8, which is actually 110 multiplied by 8. And where does this 8 comes from will be the real part of the SD earlier. And beta, we will use 0.8 divided by 55 and we will get 0.0145. So with this, we have basically realized our lead lag compensator, which has a transfer function of s plus 0.8 divided by s plus 0.0145 multiplied with the lead compensated earlier, s plus 1 over s plus 12. So just as a summary, this part will be our lead compensator, which will actually help us to solve the settling time and also the maximum overshoot requirement. As for here, this part will be our lag compensator, which will help us to settle the steady state error of 0.1. So with this combined, in terms of the calculation and on the theory side, it is able to achieve the requirements as stated earlier. However, we will always have to use the MATLAB to generate the answer, and we will see later there is actually something wrong with this, and it is not going to be result into something that we actually expect. So let's check out MATLAB on this. So in this MATLAB here, we have defined the C lead compensator, which is the same as what we have discussed earlier, and also the lag compensator, which has a 0 of 0.8 and pole of 0.145, and then this K must be equals to 1. And then we have defined our G, which is our plant, and then we define our feedback transfer function, which cascade the lead and lag, okay, with the G, and finally we generate the step response of the closed loop transfer function. So you can see that the final value is 0.99 and my steady state error will be equals to 1 minus 0.99, which is equals to 0.01, which is actually good. But as you can see here very clearly that by looking at the timeline over here, when the system is settling, it is almost indicating here is that the settling time is almost about 7 to 9 seconds, which is actually out of our requirement. So the reason why it's actually happening is that it's actually related to the dominant roots. When we actually use the approach of the lag compensator design that we actually designed earlier, our pole and zeros of the lag compensator are actually placed very near here, the origin. And then the -1 and -4 will be our original system's poles and zeros, and we have placed a 0 at -1 and we have subsequently placed a pole at -12. So the lead lag approach that we are actually using here will construct a line here and then another line here, and probably the root locus will be something like this, and then this is the location of our intended roots SD. However, based on this root locus of the lead lag compensated system, the lag compensator will introduce some dominance in here, which means now actually our SD will becomes here. And with this method, although it looks theoretically feasible, but in actual case it is actually introducing dominance which is actually far from what we expect in the lead compensator. So that means you have to pay more attention when you are actually designing the lead lag compensator, because the lag compensator will potentially change the dominance of the system. Thank you very much for watching. Bye.